Hi everybody. Hi there. I think we'll be seeing. Can we have your attention just for a few minutes before we start? I think we'll be seeing people coming in for a few minutes yet. But what I'd like to do is just have a little bit of an introduction from myself before we kick off. Great to see everybody, all the large numbers. Many faces I recognise from current years, which is good, and also two students that I recognise from induction this week, which is good to see as well. New students there, very good. Just a little bit of background for this. This is a lecture which has been arranged via the IMechE. I'm going to introduce my colleagues in a short moment, but basically, those of you who are not sure about what the IMechE might be, some students who are new to it might not be. The IMechE is the Institute of Mechanical Engineers, and that's the professional body that govern the area of mechanical engineering in practice, and also they help set standards and maintain accreditation in universities as well. It's coincidental that we're actually going through our 5-year accreditation process at the moment, and we'll be having an IMechE panel coming in November of this year. I'm hoping that some of you here will be accepting my offer to meet the panel and give you feedback on the courses that we offer you. So that's just a little bit of a comment about who's organising this. It will turn out to be, this is the first of a series of lectures. I'm not going to say too much more about that, but the rest of them, my understanding is we'll be offering them virtually online rather than in person. And we've timed this one to be the first of the series, given its induction week. And I'm glad that we've got the turnout that we were hoping for from that. So I don't think I need to say too much more, other than there are refreshments and some bits and pieces that Josh is going to pick up very soon. And that later on we'll be offering those up for anybody who wants to take them. I would like to thank Josh, those of you who have come across Josh already during induction or in your previous experience have been on the courses with us. Josh is our engagement officer, student engagement officer, excellent chap, and he's been doing some excellent work. And he's largely responsible for organising this, doing the admin and getting everything in place here. He's not here yet. He might come back in a few minutes. Certainly want to thank him. Hopefully we'll be seeing more of him in the coming weeks and months. So, without anything else to say, I'm going to introduce my colleagues. And we have Daniel Wells, who we call you Dan, yeah?
Yep.
And Brian Lawson, correct, yeah, from IMechE. I think I'm going to hand over to Brian directly now so he can make his introductions about what's going on here tonight. Thanks, everybody. Just come in and find a seat when you're ready, and I'll say no more. I'll hand over to Brian.
Okay, well, the introduction will be in two parts. Will be the informal bit that will involve me taking a photograph of you guys. If you don't wish to be in the photograph, line in the floor or stand yourself. And then I'll do the proper introductions. But just to let you know that it's 42 years since I was doing the same as what you guys are doing. So I'm a mechanical engineer, and I understand most of you guys are also mechanical engineers. Is that correct? Yeah. Nod vigorously if it's correct, please. Yeah.
We have a range of civil, mechanical, and maybe others as well, actually, I think.
Which was so electrical. Security's not working. You've got it. It's only a matter of time. Well, you've got a load of exciting years in front of you with your career in mechanical engineering. It's the best thing that I could possibly have done. I've travelled all over the world, all over this country, lived in lots of lovely places. I've ended up in Huddersfield. So, without further ado, I'm going to take a photograph with myself and Dan, and you guys in the background. Come around here, Dan.
This is a selfie, isn't it? That's...
Yeah. Smile, everybody, or hide if you don't want to be photographed. Well, there we go. painless, you see.
Right, the formal bit. The formal bit.
Is the microphone? Yeah, I know it's a microphone. That's on. That's working. Hopefully, Bilal can hear us. So, my name is Brian Lawson. I'm the technical director at a project engineering and project management company. Come in, make yourself comfortable. Don't worry. More the merrier. I'm also the immediate outgoing chair of the Yorkshire region IMechE, and I'm actively involved with the Western area, which is the Huddersfield / Halifax area of the IMechE. Tonight's lecture, Steam Fundamentals, is the first in 8. The other 7 are all going to be online over Teams. And it was about 4 years ago that I went through this program of lectures, which was about nearly 40 years since I'd been to university. And all of a sudden I thought, oh, that's how it works, is it? So it brought it all back in a way that I understood. So I'm sure you'll enjoy what Dan's going to offer tonight. The next lecture is on the 24th of September at 6 p.m. It's online on Teams. To register for it, you'll have to go onto the IMechE website, and it's called Near You. So if you just type in Yorkshire IMechE near you, it'll take you to a web page whereby you can find the Western area, and all the lectures are laid out one after another. Click on it, register, and you'll be sent the link over Teams. There's a few thank yous. Do we need to do any health and safety, fire evacuation stuff?
Just mention that we don't have anything planned for by way of demos or checks. So anything that does happen, we need to respond to it as a proper alarm and leave the building, and we'll guide you on that.
Okay, and myself and Dan will follow your good self, if that's all right.
Sorry.
Myself and Dan will follow your good self. Quickly, yeah.
We'll be running.
We're happy to take questions through the lecture. If the simple clarification, if it involves a long answer, we'll park it until the end, if that's okay. So a few thank yous. The Western Area IMechE Committee, who provide the resources to make these happen with regard to the university, and Dan. Got to thank Josh and Carl for their help organising it in the back office. And finally, my mate Dan, who does all the hard work, and this is my bit over with, one photograph, and then I stand aside and let him take over. So without further ado, you're on.
Great, thank you very much for that introduction, Brian. And I'd just like to echo the thanks that you gave to the team at the university, to your colleagues at IMechE, and also to your colleagues at Projex Solutions. Thank you for that. My name's Dan Wells, and I'm the national consultant specialist for Spirax, Sarco, UK and Ireland. It's a fancy title. It basically means I'm not a salesman. I work for the business development team at Spirax Sarco to ensure that we're offering the appropriate support to professional organisations such as the IMechE, to universities, and to design engineers that are both studying but also in practice with their ongoing educational, technical and commercial requirements. So can I ask how many of you have heard of Spirax Sarco? Not a huge number. For those of you that haven't worked with Spirax Sarco or haven't even heard of Spirax Sarco previously, we're a FTSE 100 organisation. So we're probably the biggest company trading on the stock market that the vast majority of people have never heard of. We're a British company. We do approximately 70% of our manufacturing in the UK. So don't let anybody tell you that Britain doesn't manufacture anything anymore. And we work across 3 different business streams. So I personally work for the Steam Specialties division, or the Steam Thermal Solutions team. But sitting alongside our Thermal Solutions team, we've got what we call our Electric Thermal Solutions team. When most people think about gas, or when most people think about steam, they think of the dirty fuels that have traditionally been used to generate that steam. And that's not the case, because we've got the technologies that can actually electrify our clients' existing steam infrastructure. And by doing so, that means they can move away from gas towards a fuel source that is more environmentally friendly. Essentially, it means that when we're talking to a hospital, a food and beverage plant, it means that we can help them decarbonise, yet retain their existing steam infrastructure. And then we've also got a division that includes pump manufacturers, hose manufacturers. We've actually got an organisation literally 2 minutes up the road at Bradley, Aflex Hose, that manufacture all of our PTFE hoses. Most recently, we've acquired, or should I say we've heavily invested in an organisation called Kyoto that make salt-based heat cubes that can produce thermal energy streams such as steam that are commercially viable. And we've also invested in SPH, Sustainable Process Heat, that manufacture steam-based heat pumps. As I've mentioned, as far as the series of lectures that we're going to go through in the coming weeks are concerned, we're going to focus specifically on the topic of steam. So in order to support you with your studies, we've got a very, very powerful range of resources that I'd encourage you to take a look at on our website. Some very, very powerful learn about steam tutorials. We've got a very active YouTube channel which will demonstrate different technical concepts surrounding the steam and condensate loop in quite short, punchy animations. And we've also got a range of calculators and configurators that are available both on the website, but they're also app-based as well. And those calculators and configurators can be used for two different reasons. So we can use those calculators and configurators for design purposes. If we know how much heat energy a process requires, well, by default, we've calculated how much steam is needed. We know the size of the heat exchanger. We know the size of the steam pipework, the condensate pipework, the steam traps, the control valves, the condensate pumps. But we can also use those calculators and configurators to calculate our client's cost of steam. When we're generally talking to a steam user, a hospital, an oil and gas plant, whatever it may be, I would anticipate around 50% of our clients have got a really good understanding of what their cost of steam is. 25%, they probably hold their hand up and they say, we've got no idea what our cost of steam is. Can you help us with that? What's most worrying is that the remaining 25% of those clients, they will tell us they know what their cost of steam is, but they will be way off the mark because they're probably basing that information on the cost of gas from 5 years ago. And as we know, since the war in Ukraine, the cost of gas is somewhere between 3 and 3.5 times what it was. So if our client is basing their cost of steam on the cost of gas from 5 years ago, they're way off the mark. So that's really is one of the first questions we want to understand, the cost of steam. If we know our client's cost of steam as a starting point, we also have indirectly calculated the carbon emissions. And driving down the cost of gas and the cost of steam is often secondary to our client that's got their goal of decarbonising their thermal energy. So if we're engaging with an existing steam using client, if we help them to generate the steam, distribute the steam, and use the steam at the process more efficiently, the boiler doesn't have to work as hard. We're not producing as much steam. Our cost of gas, and more importantly, our carbon emissions are going to be driven down. They're going to be significantly reduced. But we can only demonstrate what that benefit is if we've understood the cost of steam as a starting point. So the series of lectures that we're going to go through in the coming weeks is going to give a very full and detailed tour of a typical steam and condensate loop. And many of you may be thinking, is steam really relevant? Isn't it a Victorian hangover? Isn't it dirty, dangerous to engineer? And the reality is steam's very, very relevant because steam is currently used in the vast majority of every product that is currently being manufactured, whether it be in the UK or around the world, all the way from the food and beverage, the pharmaceutical, the chemical, the oil and gas, power generation, hospitals, universities use a significant mass of steam. So it's still very, very relevant. So when you hear people in industry talking about de-steaming their process, 9 times out of 10, they don't actually mean de-steaming. They don't mean a move away from steam. They mean a move away from those fossil fuels that have traditionally been used to generate that steam. So the presentations that we're going to go through in the coming weeks, they're going to go through steam from the cradle to the grave, really. We're going to end up by examining how we can generate steam from renewables, from heat pumps, from thermal storage devices. But before we get to that point, it's prudent to start with the basics and go through the fundamentals. So as far as the fundamentals of steam are concerned, I'm going to start off this evening by talking about the basic terminology that we use. Loop. We always refer to a steam system as being a loop. In a typical or a traditional steam system, we could have 1 or more, anywhere up to 6 horizontal fire tube steam boilers. Spirax Sarco don't manufacture steam boilers, but we do manufacture the vast majority of the controls that sit around the boiler house to ensure that the best condition of steam is generated at the best possible quality and condition, as efficiently as we can. We don't want to burn too much gas, but most importantly of all, to ensure that that boiler is operating safely. We've got the gas that comes in to a burner at the side of the boiler, and we're going to have a number of different fire tubes that are zigzagging throughout the boiler, typically 3 passes. So that's what we would refer to as it being a 3-pass boiler.
You could, just for the benefit of the audience, you couldn't sort of give an idea of physically how big typical boilers are?
This is what we call a fire tube boiler. And a fire tube boiler has got the combustion gases, the flames, if you like, running through the water that's held in storage. In larger industrial processes, typically where steam is generated at a huge mass, but at very, very high temperatures or pressures, we could have the opposite, which is what we call a water tube boiler, which is where we've got tubes of water falling vertically through what is essentially a furnace. As far as the fire tube boilers are concerned, this is what you will commonly find in the hospital up the road. You'll find them in a lot of the food and beverage processors. You'll find them down at the chemical plant down on Leeds Road, for example. The horizontal fire tube boilers, they're really limited by the road network. So if you can imagine one of these boilers being transported down the M62, it's limited by the capacity or the load that is permissible on the road. So that would be around, you'd be talking about a steam production of approximately somewhere between 25 and 27 tons per hour. So imagine that, between 25 and 27,000 kilograms per hour of steam. And it's by no means unusual for an industrial process to have a bank of up to 6 of those.
No, that might be as big as a 4-berth caravan or something like that, physically, round about that sort of size.
Potentially even bigger. So you're going to have like potentially a 3-meter diameter. So once we've, I'm going to use the example of a steam boiler operating at a pressure of 10 bar. So a 10 bar gauge, we're potentially going to have combustion gases at about 1600 degrees that are causing the water to boil off. And then we're going to have gases, the combustion gases exiting the boiler and going up the stack into the chimney at approximately 200 degrees. Some boilers might have what we call an economizer on the stack, taking a little bit of heat energy from those combustion gases, so we can put that back into the water before it goes into the boiler. So we've got to put a lot of energy into the water, not just to bring it to the boil, but also so that that water is going to boil, evaporate, change state from a liquid to give us steam as a gas. So the space at the top of the boiler that's shown in red, that's the space that exists to allow that expansion to take place. Remember, this boiler is operating under pressure. I'm going to use the example of 10 bar gauge. The reality is, in industry, a typical horizontal fire tube boiler, that'll be working at pressures typically between 7 bar and 12 bar gauge pressure. So when we're talking about steam, I'm going to call it a gas just for ease. With steam being a gas, it's compressible. So the higher the pressure, the smaller the volume that steam is going to occupy. So if we've got a high pressure in the boiler, we've got two benefits. We've got the steam with a very small volume, meaning we can now distribute it a considerable distance in a very small pipe diameter. So if you think about the hospital up the road, or if you think at the chemical works down on Leeds Road, we could be distributing that steam thousands of meters. So if we can distribute high pressure steam with a small volume in a small pipework, there's a huge financial benefit to us. The other benefit of high pressure steam is we've got a lot of motive energy that is pushing the steam out of the boiler into the pipe and sending it thousands of meters to a plant room, to the point of use. Now, in the vast majority of building service and industrial applications, we're going to be using the steam for its thermal energy attributes. We're using it to heat something up. So at the opposite end of the pipework, 1,000 meters away, I'm showing a very simple, basic plate heat exchanger. So the steam as a gas is brought onto the top of the heat exchanger. The steam will pass down one side of the heat exchanger, and the water, or whatever it is that we're heating up on the secondary side, is going to run counterflow to take on all of the energy that the steam is carrying. Now, when steam gives up its heat energy, it condenses. That basically means it changes state from a gas to a liquid, so its volume collapses significantly. When that happens, the steam gives up its heat energy, it changes state from a gas to a liquid, but it doesn't cool down. So that condensate exists at exactly the same pressure and exactly the same temperature as the steam. It's just got less energy in it. And condensate's a byproduct, it's unwanted. We need to get it out of both the distribution pipework, and we need to get it away from the bottom of the heat exchanger as well. Because if we don't, that condensate is going to back up, it's going to flood the heat exchanger. We've got a barrier to heat exchange, or it can flood the distribution pipework as well. And that's why we drain the condensate away from the bottom of the heat exchanger. Steam coming in at the top, and the pressure within the steam heat exchanger is also helping to push the condensate away. So the pipe in green, that's much smaller than the connecting steam pipe, because we know condensate is a single phase, non-compressible liquid. So we get that condensate out of the heat exchanger as quickly as we can. The problem is, once that condensate's gone, we need to make sure that we're not losing the steam as well. That's why we've got a steam trap that's located very close to the heat exchanger itself. Think of a steam trap as being an intelligent non-return valve. It's capable of telling the difference between the steam as a gas with that high energy content and the condensate as a liquid with very, very little energy present within it. It can tell the difference between the two. So when there's condensate present, the trap will be open. And when the condensate's gone, the trap will close to prevent that inefficiency. And therefore, the boiler doesn't have to work as hard. Our cost of steam, our cost of gas, and our carbon emissions are going to be kept to the absolute minimum. So a steam trap's a passive device. We need a pressure drop across the steam trap. In other words, if we've got a pressure of 1 bar gauge within the heat exchanger, we need the pressure less than 1 bar gauge downstream, so the steam is capable of pushing the condensate away. So at this point, we should hopefully have a little bit of pressure within the condensate, and that's going to help the condensate move Ideally, all the way back to the boiler house again, if not to some form of a reservoir where we can pump that condensate. So whilst condensate doesn't have a great deal of energy present within it, it's still high temperature hot water, and it's chemically treated hot water as well. So if we can bring that condensate back from the heat exchanger all the way back to the boiler house, that high temperature hot water is giving us a really good head start to produce steam again as efficiently as we possibly can. So that's why we've got the term loop. Steam as a gas with a high energy density leaving the boiler, moving towards the heat exchanger, the condensate as a liquid with a very high temperature coming back. So when we think about a steam boiler house or a steam distribution system, we need to remember the differences that steam has compared to a traditional hot water-based heating system. And we need to ensure that the system is designed accordingly. Those differences are going to give us a lot of benefits and advantages. Remember, steam's a compressible gas. High pressure steam, small volume. Small volume, we've got a small pipe infrastructure and we don't need to pump it. One of the fundamentals that sets steam aside from hot water is the fact that steam's got a pressure-temperature relationship. If we know the pressure of the steam, we know its temperature. If we need to achieve a particular temperature at a process, we can bring that around very, very easily by a very, very simple set of controls. Typically, it's a pressure reducing valve. We know the pressure, we've controlled the temperature. But it also tells us that we need a really good number of pressure gauges around a steam distribution network. Without those pressure gauges, we've got no understanding of what we're working with. Steam's got a very, very high energy density compared to water. Because steam gives up its heat energy by condensing, and because water gives up its heat energy by cooling down, it means that we can get the energy from the steam into the process very, very quickly. It also tells us that we've got approximately 50 times more energy present within a kilogram of steam compared to a kilogram of water when that water's circulated across a heat exchanger, for example. So, of course, with the steam system, if we're comparing a steam boiler to a hot water boiler, the steam boiler is significantly smaller in space and it can generate a greater mass of energy more rapidly. We've already mentioned we don't need pumps with the steam system. The steam's a gas, it moves in accordance with the pressure drop around the infrastructure. Water-based systems, whether they're produced by a gas-fired boiler or by heat pumps, they will need a much, much larger infrastructure because it's got a reduced energy content, it's got a greater volume, but we're also going to require those circulating pumps as well. Not so with steam. Steam gives up its heat energy by spreading out across the heat transfer surface area very, very rapidly. When we depressurize the steam at the point of use in order to control the temperature, depressurizing the steam is going to expand. So it's going to spread across the entirety of the heat transfer surface area without leaving us with cold spots or striations like we commonly see with water-to-water heat exchangers. And because steam gives up its heat energy by condensing rather than by cooling down, the speed at which that high energy density can get into the process is about 3 times more rapid. I think one of the critical fundamentals that we need to get across when we're talking about steam systems is that phase change. When steam gives up its heat energy, it condenses, it changes state from a gas to a liquid. That liquid condensate is going to exist at exactly the same temperature. So it's critically important that we don't fall into the trap of confusing the point of energy with temperature. They're 2 completely different issues. That condensate will exist at the same temperature as the steam, but because it's got far, far less energy contained within it, it needs to be considered as a byproduct whenever it's in the pipework or in the heat exchanger itself. So I'm going to ask Carl, have the students covered off the steam tables yet?
It would very much depend on which part of the course they're at. But I've got to be honest with you and say it's not something that's very common these days.
Right, okay. Brian will tell you that this is the single most important slide that I ever show. And Brian will probably also tell you that if you're going to attend all 8 of my lectures, you'll be sick to death of this slide. The steam tables, critically important, vitally important. They bring together a lot of information. So if there's only one slide that you're going to pay attention to this evening, this is the slide. The first 2 columns that you can see here, that brings together that pressure-temperature relationship that we spoke about. So I want you to think about generating steam in a kettle in your kitchen. We take 1 kilogram of water, 1 litre of water. That's got a volume of 0.001 cubic meters. We put that water into our kettle, we bring it up to the boil. And we know from basic maths and physics that at atmospheric pressure, 0 bar gauge, water boils at 100 degrees. And therefore, the temperature of the steam that's produced is also 100 degrees. So when that kilogram of water is boiled off and changed from a single phase non-compressible fluid to steam as a gas, the rate of expansion is more than 1,600 times. It's huge. So the magic's really happening in these 3 middle columns. It shows us the energy relationship that steam has. The first column, this shows us how much energy the water needs to contain before it boils. Now, notice here I say how much energy the water contains. It's not how much energy we add, because we could be putting a block of ice into the kettle, or we could be putting water at 90 degrees into the kettle. The colder the water, the more energy we've got to add. The more gas we're burning, the higher our cost of steam, the greater our carbon emissions. So that really explains the benefit of getting that hot condensate back to the boiler house if we can. But we've only got boiling water here. We want steam. So the next column shows us how much further energy we've got to put to the boiling water to make it evaporate and change state and give us steam as a gas. So the final column, that's the total energy content of the steam. Basically, the sum of the previous 2 columns added together. Now, remember what we said. In reality, our client's generating steam under pressure. So at 10 bar gauge, because of that pressure, the boiling point is higher. Therefore, the temperature of the steam is higher. Because of the pressure, the water's got to contain more energy before it boils. We don't need to add as much energy to that boiling water to make it evaporate, but the steam has still got a higher total energy content. And of course, because of the pressure, we've really compressed the volume of the steam. So it's now really cost effective for us to distribute it a long distance in a small pipe diameter with a lot of motive energy to it. But look what happens here. When we've reduced the pressure 1,000 meters away at the heat exchanger as a means of allowing the steam to move and as a means of controlling the temperature, there's actually more useful energy present within it. So the enthalpy of evaporation, that's the energy we need to put into that boiling water to make it change state. Well, that's also the energy that is capable of moving across the heat exchanger to heat the process up. So if you've got steam tables at home, or if you've got steam tables that you refer to for your college, I'd probably put a line through that enthalpy of can't even say it, enthalpy of evaporation. Call it the useful heat energy. Now, the problem we have with the steam tables is, academically, they're a fantastic resource. In the real world, the problem with the steam tables is they assume that the steam that is being produced on our client site is 100% dry 100% of the time. And it never is. So if we move across to the graph at this side of the screen, this is what we call the temperature enthalpy curve. And it plots the journey that that kilogram of water takes When it boils off, when it changes state from a liquid to give us steam as a gas. 0 bar gauge, water boils at 100 when it contains exactly 419 kilojoules of energy. Any more than that, and it starts to evaporate and starts to boil off and produce steam. But we're only going to get dry saturated steam, which is the value that is shown in the steam tables. We're only going to get dry saturated steam when we've added 100% of the energy in this column to 100% of the energy shown in that column. That's when the steam tables are 100% accurate. Now, in reality, poor boiler control and poor working practice in how the steam's moved means that the steam could exist in what we call the wet steam zone here. Wet steam is going to create a number of problems on our client sites. And we split those problems into 2 areas. First of all, the mechanical issues, the maintenance issues. If we've got wet steam, we're more likely to experience corrosion of the pipework, pinholing, damage to capital equipment. The steam's going to carry specks of rust that's going to create erosion of controls such as control valves, pressure reducing valves, or flow meters. When that steam is carrying specks of moisture, we're going to get further erosion to those same controls, corrosion and erosion. But we're also going to get water hammer. Are you familiar with the term water hammer at all? Think of a steam pipe. If we've got any moisture or condensate that exists in the infrastructure, if we're moving that steam, assuming that it's a gas, as the steam tables do, we could potentially move that steam at a velocity of 40 meters a second. And that's about 90 miles an hour. But if we've got any condensate that's present in the bottom of the pipe as a liquid, we can't move it at anywhere near the same speed. The steam is going to push the condensate into a solid slug. There'll be a buildup of pressure, and that water will be pattered around the infrastructure, creating a lot of noise, vibration, and damage. And in extreme circumstances, it can even result in pipework being ruptured. Something that the health and safety executive take very, very seriously. So aside from the mechanical issues, the erosion, the corrosion, the water hammer, it's also likely that we're going to experience inefficiencies. So remember, we've got steam at 10 bar gauge, 184 degrees, leaving the boiler, coming into the pipework, traveling 5,000 meters around our client's site. It's a carbon steel infrastructure. We're going to have missing, damaged, substandard insulation. That pipework's one big radiator. We're going to get a lot of heat loss. So we could be putting 10,000 kilograms of steam into the pipework. We're not going to be getting 10,000 kilograms out at the other side. We might only get, for example, 9,000 kilograms available because 1,000 kilograms of steam is condensing in the pipework. And we've got to get rid of that condensate for reasons we've mentioned, those mechanical issues. So we're going to need to install a greater number of steam traps to drain that condensate away. So that's what we refer to as steam starvation. It's an inefficiency. If we know how much steam is going missing in the pipework as a result of that wet steam, well, the boiler's got to work harder. Our cost of steam, our cost of gas, and our carbon emissions are going to increase. The other thing to bear in mind is if you think of that steam pipe, think of the cross-sectional area of the pipe. The condensate is going to fall to the bottom of the pipe as a liquid. Steam is going to move over the top of that condensate. And as it does, it's going to degrade. It's going to deteriorate. It's going to get wetter and wetter. So it's going to move further from the dry steam line into what we call the wet steam zone. And if you look at the bottom axis on the graph here, that represents the energy content. In other words, the wetter the steam, the less energy the steam has. So there's a double whammy going on here. We've got a reduced mass of steam available as a result of the heat loss in the pipework, and the steam that is available, it's got less energy. So that tells us that either the heat exchangers are now undersized and the process time is going to extend, or the boiler's got to work even harder to produce even more steam. So our cost of steam, our cost of gas, and our carbon emissions are going to escalate further still. So it's critically important that we do everything we can to ensure the steam condition or the steam quality stays on or as close to that red line as we possibly can. Not just for maintenance issues, not just for process time issues, but also for those inefficiencies. The cost of steam is critically important. And it's something that you'll keep hearing me rattling on about in future presentations. So pulling together those relationships, kilogram of water, 0.001 cubic meters, boils off to give us steam as a gas at 0 bar gauge, and it expands by 1600 times. Under pressure, the steam's got a much smaller volume. And when we let the pressure down at the heat exchanger, that steam is going to expand significantly. So I want you to think about those steam traps now, because the steam trap is vitally important. It's a critical piece of capital equipment that allows the condensate to drain away and it allows the steam to stay dry. We need that pressure drop across the steam trap so that the condensate can move. The problem we're going to have is if a steam trap fails in the open position, the pressure drop can be far, far greater than we're expecting. So we're going to get very high pressure steam with a small volume, depressurizing and expanding to a huge volume. That condensate pipework's been designed to move a single phase non-compressible fluid. So if we've got a huge expansion going into that very, very small pipe infrastructure, it's going to create a lot of damage. So we're going to see what we call steam vents sited periodically around the infrastructure. The purpose of those steam vents is to prevent that damage from taking place. And another relationship I want to refer to is what we call the pressure temperature relationship. So as we've mentioned, water at 0 bar gauge boils at 100 degrees, tells us the temperature of the steam. At 10 bar gauge, water boils at 184 degrees, therefore so is the steam. But if we've got a heat exchanger that needs to operate at 130 degrees, for example, it tells us that we can achieve that just by manipulating the pressure with those very, very basic controls. Remember what I said, when steam gives up its heat energy and condenses, it doesn't cool down. So this is the pressure temperature relationship for both steam and for condensate. That tells us that when the condensate, when that liquid is under pressure within the pipe infrastructure, it can exist as a liquid at 184 degrees. But we know that if we drop the pressure down, that liquid cannot exist at 184 degrees at 0 bar gauge, for example. So if we think back to that failed steam trap, we've got two things happening. We've got the steam that is depressurizing and expanding. We've got the liquid condensate that is depressurizing. And as that condensate depressurizes, a certain mass, a certain percentage needs to boil off and expand and change state back to steam again. So that rate of expansion is going to be even greater. And that really explains why we need to vent that steam away, to prevent that vibration taking place, that damage taking place in a very, very small infrastructure. Unfortunately, those steam vents, they're a necessary evil. We've got to protect the infrastructure while those vents are throwing steam into the car park. We're heating the car park up. The boiler is racing to replace that missing steam. Our cost of steam, cost of gas, and our carbon emissions are just escalating. So those steam vents, they really are one of the very, very first things we want to look out for to understand the health of the wider steam trap population. So I'm going to skip very, very quickly now through very basic steam generation. So we're going to be installing those steam boilers. It can be anywhere between 1 and 6 in number in those horizontal fire tube boilers. It's typically at the corner of our client's campus for logistical reasons. And that means we can then be distributing the steam, what could potentially be thousands of meters around site. So it's vitally important that we control the condition of the steam as accurately as we can, so we don't have too much of that wet steam condensing in the pipework, and so that we can keep control of those mechanical issues and those inefficiencies. So there are a number of different controls and ancillaries that will furnish the boiler. There are many, many different types of boiler controls, level controls, water chemistry controls, safety controls. And the function of these controls is really to ensure that steam's being produced very rapidly and responsively, to ensure that we're producing the steam with a minimum of energy consumption. We want to keep the gas to an absolute minimum. We want to keep the quality of the steam as dry as it possibly can, so it exists at a condition that's as close to that red, dry, saturated steam line as we can. Most importantly of all, we need to keep the boiler operating safely. So one of the most important components in the boiler house is what we call the hot well, the feed tank. This is where we want to contain all of that hot water that we're bringing back from the various points around site to the energy centre, and we hold it in storage. Typically, the capacity of the hot well is 1 hour's steaming capacity. So if our client is producing 20 tonnes of steam per hour, that hot well will need to hold 20 tonnes of water. And we want to keep that water at the highest possible temperature. The sweet spot is really 85 degrees. Any higher than 85 degrees, and some of that hot water is likely to boil off and produce steam as it falls in pressure when it's drawn across the boiler pump. It's going to create quite an expensive problem for our client. That's why we vent any excess of energy away from the hot well to prevent that over temperature. But if it's any lower than 85 degrees, then we've got to burn more gas. Our cost of steam and our carbon emissions are going to increase. But as another consequence, it means if we've got cold water, it's going to create more corrosion of the boiler. There's more water that is, there's more gas contained in colder water than there is in hot water. So our client's going to add a little bit of water chemistry at this point in order to purge off any oxygen and gases. But of course, the more chemicals we're adding, the more our cost of steam is going to increase. And we're also changing the water chemistry. So other things we want to think about in the boiler is the way the water level is being controlled. Think of that steam boiler as being a giant can of Coke. We fill it 80% full of water, we lie it on its side. When that happens, if we know the exact water level within the boiler, we know the surface area of the water. So we know the velocity that the steam is leaving the boiler at. Now, if the water level fell or rose significantly, that surface area is changing, which means the steam can be leaving the boiler at a different velocity. And in extreme cases, it can carry more of the water out of the boiler and into the pipework. And that's really going to create those inefficiencies and those mechanical issues we spoke about. So in order to control the water level, we're going to need a variety of different level controls, sending a signal to a pump. Ideally, we'll be operating the boiler with a modulating feed pump that's constantly circulating a ring main of high temperature hot water around the boiler house. And we'll have a capacitance level control probe, which means that that boiler is capable of operating at a consistent water level. The water coming into the boiler will be in equilibrium with the steam leaving the boiler. In order to maintain the water chemistry, we perform what we call blowdown. So if you think of a steam boiler think of it as a cup of tea. So we put a spoon of sugar into the tea, we put a spoon of sand into the tea. And that represents the different cocktails of chemicals and minerals that are going to be present within the water locally. Some of the chemicals will dissolve, like the sugar, and some will just form as a particulate at the bottom of the boiler, like the sand. So we need to address both. So we perform what we call bottom blowdown. Bottom blowdown is performed by, we crack open a little valve, and the water that's within the boiler at 10 bar gauge, 184 degrees, as it falls in pressure, moving across that valve, it's going to perform a very, very violent blast action. And that means that a lot of the sediment that sits at the bottom of the boiler is going to be blasted away. We need to take it to waste. It's high temperature hot water. But for every kilogram of water we're putting to waste, we've got to consume the same kilogram of much, much colder water from the hot well. So if that hot well is sat there at 50 degrees, for example, as opposed to 85 degrees, we've got to burn a hell of a lot of gas in order to bring that boiler back up to the boiler gate. So we want to ensure that we're performing the absolute bare minimum of blowdown required. And that hot water, it's got to go to waste. We can't reuse it anywhere else. But it can only go to waste at a temperature of 43 degrees. Any higher, and we're in breach of the Water Treatment Act of 1990. So we put the water to waste, but before it goes to effluent, it goes to a blowdown vessel. And that blowdown vessel essentially contains that hot water, and it allows it to cool down before we can purge it to waste in a few hours' time, once it's cooled down organically. But the main reason that blowdown vessel is, if we've got hot water at 184 degrees coming out of that boiler, as it depressurizes, we're going to have that huge violent expansion. So it needs to be capable of allowing that steam to boil off and expand and be safely vented to the sky. Unfortunately, there's no opportunity for heat recovery here. The best we can do is to keep that blowdown to an absolute minimum. But using my analogy, the bottom blowdown, that takes care of the sand in my cup of tea, the heavier particulate. We need to address the high water chemistry with the solids that are going to be held in suspension. That's what we call the TDS. We could perform the TDS manually. Better for us to do it automatically. If we do it automatically by means of having a conductivity probe, sending a signal to a modulating valve, it means we can ensure that that valve opens at the determined set point in terms of part per million. Now, if we allow the TDS level to rise to a very high concentration, we're going to get a lot of foaming present that sits on the surface of the water. And as the boiler fluctuates in pressure to keep up with the demand, that foam is going to expand and it's going to be drawn out of the boiler and into the pipework. That foam is going to be very, very wet, sticky. It's going to result in a poor condition of steam. That foam is going to dry out of scale. It's going to create erosion of sensitive areas. It's going to bind itself to heat exchangers, resulting in a barrier to heat exchange. But if we're blowing down too much of that hot water to waste, we're going to have a huge financial inefficiency. Now, unlike the bottom blowdown that's got that grit and that particulate in it, there is an opportunity for a little bit of basic heat recovery with a TDS system, because we're not going to have any aggressive particulates that could result in erosion. We can take that heat energy away and potentially add it back to the hot well. So if we've calculated our client's cost of steam, cost of gas, we can guarantee what that payback is likely to look like. What's quite often overlooked with traditional steam boiler houses is they're not going to meter or monitor the steam that is being generated. And that's critically important, because if we don't know how much steam the boiler is producing, we can't calculate that cost of steam. We don't understand the carbon emissions, and we don't understand how efficiently that boiler is operating. And by metering at each heat exchanger 1,000 meters away, it means that if we know how much steam we're putting into the pipework and how much steam we're getting out, we know how much steam is going missing in the middle. And that can be an indication of one or more failed steam traps, but it can also be an indication that we've got very, very wet steam that is condensing out in the pipes. So when we're talking to a steam using client, they've got a lot of responsibilities to ensure that their boiler house is operating in accordance with the appropriate standards. For me personally, INDG 436 is the important one. INDG 436, think of it as a risk assessment. So that helps our steam using clients understand what their responsibilities and obligations are in order to keep that boiler operating safely. Now, underneath that standard, there's a series of guidance documents. We call them the BGs. And these are written and administered by the Combustion Engineers Association in accordance with the Boiler Operators Accreditation Scheme, with oversight of the Health and Safety Executive. The thing to bear in mind is the Health and Safety Executive in particular, they don't care if our client has got a poor condition of steam that is resulting in an excessive wear and tear of different items of capital equipment. They don't care if that steam is contaminating a process or a heat exchanger. They don't care if the boiler's not capable of responding quickly. They don't care if our cost of steam, cost of gas is high. Not their problem. All they care about is that that boiler is operating safely. And that really explains why there are so many different boiler control types. It depends what the client has got an appetite for. And because the boiler industry is very, very competitive, unless a design engineer understands the basics of boiler controls, it's highly likely that that boiler manufacturer is going to offer a boiler that operates on the cheapest is best principle. And the client could then encounter a significant burden of maintenance or a high cost of steam and also significant carbon emissions. The good news is, if we've calculated the cost of steam, we can guarantee what the benefit is to the client by upgrading those boiler controls in many instances. So think about it. We need to keep the condition of the steam as dry as we can. Otherwise, we're going to encounter all of those issues. The problem is, once the steam leaves the boiler and moves into the infrastructure, it's got to move round that radiator. Best chance we can have of ensuring that the steam gets to the processors 5,000 meters away at the best condition is by producing the best condition of steam here. Now, I think it's next Tuesday, is it, Brian? We've got the presentation. We're going to move on and we're going to look at the design considerations. In other words, now we understand the importance of keeping the steam dry. We're going to understand how we then need to design the infrastructure so that we're moving the steam from the point of generation to the point of use to keep it at its best possible condition. So just one thing I'd just like to bring to your attention before I hand back to Brian is those of you that are very, very new to your mechanical engineering careers, please do feel free to check out our website. We've got a very detailed, it's what we call our early careers page. So that can support anyone that's interested in applying for a year in industry. It can support anyone that's interested for applying for a graduate position. So please do feel free to check it out. You can see the link on the bottom there. It's very easy to navigate to on our website. And like I say, we've got a number of different manufacturing, R&D, operational companies that are located around the UK. And it'd be a great opportunity for you guys to check that page out. So on that note, I'd like to thank you very much for your time. What I would say is if you'd like a PDF of the slide deck that we're going through or the presentation that we've gone through tonight, it is a CIBSE accredited CPD presentation. So if you'd like a copy of that certificate for your personal development folders, then please feel free to just drop me a message on LinkedIn and I'll make sure that you get a certificate and a PDF copy of that slide deck. So thank you for your attendance tonight. Hopefully it's inspired a little bit of interest for you to continue with the series of presentations. And with that in mind, thank you to Carl, Josh, everyone at the uni. Thanks to the IMechE, and most of all, thanks to Brian.
Thanks, Sam.
Any questions?
Yeah, we'll sort that out in a second. I just wondered if we have any questions, though. I think we have delivered an explicit option for that.
Absolutely.
I have a couple, but does anybody else? Okay. I was just wondering about, could you be a little bit more explicit about the issue around not being able to generate any heat from the bottom blow-off? What's the specifics?
Best working practice in the boiler guidance documentation states that hot water, because it's got so much energy in it, then we need to pass it to a vented vessel so that hot water can depressurize and expand and be put into the sky as safely and as quickly as possible. So 7.5 meters typically needs to be away from the boiler. Any more and there's a risk of a pressure imbalance. But also it's pretty nasty stuff. Yeah, it could have a lot of sediment and scale in it, which in turn could cause a sensitive heat exchanger to block up very, very quickly. So the best we can do in terms of keeping the energy and mass balance in place is keeping that blow down to an absolute minimum. We don't want to be too heavy-handed with it. So rather than blow down manually, because my 5 seconds could be completely different to your 5 seconds, that could have a huge consequence financially. The best thing we can do is to put a timer on an actuator, and by knowing the boiler pressure, the orifice size of the valve, the number of seconds it's in the open position for, we know how much energy we're blowing out of the boiler.
Thank you. Yeah.
But there's problems with the steam condition that comes out of the boiler. So let's say we are having wet steam out of the boiler. Why not have are there measures in place to maybe just heat that steam up a bit more?
Yes, that's what we call superheated steam. For example, if you had some form of secondary heating element in the steam pipework as it leaves the boiler, like an electrical heater, you would create superheated steam. Superheated steam is absolutely the right thing to do in certain environments. When we're talking about a typical or traditional steam system, we're typically using the steam for heat exchange purposes. The only way steam can give up its heat energy is by condensing. So the steam needs to give up its heat energy and change state very quickly. If that steam's very, very dry, there's a lot of energy present within it, but it doesn't want to give it up. So that means the heat exchanger is now undersized. So the only areas where we would really welcome superheated steam are power generation, where it's going across a turbine, because we don't want to get turbine blade erosion, or if we're distributing that steam tens of thousands of meters, like in an oil refinery. Because if we had very, very wet steam and we were moving it a significant distance, we'd have more of the erosion, corrosion, water hammer issues. We'd need more steam traps. So to generate superheated steam and move it thousands of meters, we would then de-superheat it by putting a spray of hot water into it when we get it next to the process. So when you're talking about food, beverage, pharmaceutical applications, de-superheated steam is actually unwanted because it can slow the process down. But we can also encounter damage to capital equipment like drywall erosion. We can also experience undersized heat exchangers, and it can mean that certain processes fall out of specification. For example, sterilizers, retorts, autoclaves. If there's too much superheat, it means that we can have batch failure of a process.
Great, thank you.
Dan, you couldn't give us an indication of approximate cost of a ton of steam. Yeah, have you got any ballpark figures?
Okay, I was in the west coast of Ireland yesterday, and they were talking about producing steam at they were talking about 55 euros per ton. They've got an excellent quality of water over there, so it doesn't need chemical conditioning quite as much, which means they don't have the same blowdown and efficiency. Same up in Scotland, excellent water, No coincidence that the distilleries are based up there. It's not necessarily because of the quality of water that's going into the whiskey. It's because of the chemical imbalance and the benefits of operating the steam boiler up there. It varies on where they're using the water from. Is it borehole water? Is it river water? Is it reclaimed water? How they're chemically conditioning it. If you were looking at the hospital up the road, I would estimate that they're going to be around £65 per tonne. I don't know that for a fact. It does vary. But like I say, that cost has increased significantly over the past 3, 4, 5 years. So we just need to ensure that whenever our client's thinking about the cost of steam, the big one is the gas. The next one is the water. The one after that is the chemicals that go into the water. The one after that, it's the pressure that the boiler operates at. And then it's the efficiency of the gas burner that sits on the boiler itself. If we know all of those values, then we can calculate the cost of steam for our client.